Hey everyone, we're CabbageJumbleAya, and we're here to count your cabbage. Next slide, please.
I bet if I gave you this wheelbarrow of coins to count at our first presentation, you'd either still be counting them now and be super tired, or you'd be out $30 on an Amazon coin counter and still have wasted a bunch of time. Luckily, in those last 4 weeks, our group has made a much easier solution. Next slide, please. Our neural networks takes as an input a bird's eye view photo of coins and outputs the total sum of coins. An example of our neural network output is shown on the right. So although this problem was comedically inspired for paying for things with the wheelbarrow of coins, it actually does have real world benefit and it helps those who are visually impaired and struggle with fine motor control. Next slide, please.
This is a brief overview of our data collection and processing pipeline. Let's zoom in. Next slide, please. First, we collected square pictures of coins on white backgrounds using our phones. We passed these through our OpenCV auto segmenter that identified each coin's contour and circled them. Next slide, please. Unfortunately, there were some errors, such as double counting toonies. We fixed these with some graphic user interfaces we made. Next slide, please. Using these GUIs, we manually corrected the segmentation circles and labeled the data by value and heads versus tails. We scaled the images down to reduce the amount of computation on each image, but still kept the images human readable. Next slide, please.
Our group took roughly 500 images and performed rotations to augment this to around 2,000. The table shows the number of coins per each coin type. As we can see, it's roughly uniformly distributed with no one coin or class lacking, which is as desired. Next slide, please.
We have even more data augmentation. We implemented Mosaic and Jitter. Mosaic combines the images into one certain ratio, and Jitter changes the hue, saturation, and brightness values of the photo. And that's it. Next slide, please.
Here's an overview of our baseline architecture. We started with the OpenCV auto segmenter before, then isolated and rescaled each coin before sending them to our basic classification CNN. Next slide, please.
So to improve upon our baseline, we implemented a state-of-the-art architecture called YOLO. As a whole, YOLO simply takes our image as an input and outputs an array consisting of the bounding box locations and the coin type. Finally, from the array, we can get the final value of the coins. Next slide, please. So what is YOLO? At a high level, YOLO uses a sliding window and scans through an image. So think of a really powerful CNN. When it detects an object, it returns a classification array and the prediction values. Next slide, please. So the problem with the sliding mechanism is it isn't very efficient. So with the help of GPU parallelization, YOLO is able to run the mechanism on divided grid cells simultaneously. And each corresponding grid cell will have a corresponding array output. Next slide, please. But the secret to YOLO version 4 is its architecture. YOLO version 4 consists of mainly 3 parts: the backbone, the neck, and the dense prediction. The backbone can be any deep convolutional network and is responsible for generating the first feature maps. In our case, we use the darknet model, which is pre-trained and 53 convolutional layers deep. The neck further distills these feature maps. And finally, the dense prediction turns these feature maps into classification predictions and bounding box locations. Next slide, please.
So first, considering the high level, the overview accuracy is the measure of performance for the goal of the project, which is the sum of coins. We aim to minimize the difference between the sum of the prediction and the ground truth coins. The ideal result is 0, and the larger numbers are worse. So to better understand the model's performance for the overview accuracy, go back a slide, I'm not done.
Sorry about that.
To better understand the model's performance for the overview accuracy, we break it down into the segmentation and the classification accuracy. The segmentation has 2 portions. The modified dice coefficient uses the intersection area over the union area to give a measure of how good a fit a prediction box actually matches with its ground truth box. On the other hand, the matching accuracy is a measure of how well YOLO can produce a 1-to-1 matching for each prediction box to a coin. Lastly, the classification accuracy is the standard number of correctly labeled over the number of matched coins. Next slide, please.
So our YOLO model performed better than our baseline model. We had very strong segmentation results, and the classification accuracy was strong as well, but not as pronounced. We learned that contextual information is important. Our baseline ignores size, which may lead to its poorer results. Our YOLO model retains this information. From that, we can infer that a very simple CNN is just really bad at generalizing. Next slide, please. So here's an example where all the values match up and the bounding box is appropriate. The image is well lit, there's very little angle skew and the coins are not touching. Next slide, please. So here's a bad example where the 5-cent heads was predicted to be 10-cent heads. Two potential reasons for this might be because the image is not as crisp as a good example, and for the coins under 25 cents, they all have the same heads. Next slide, please.
Would we trust our model to manage the world's financial systems? No, but we did learn some important lessons. First, labeling different looking images as one class leads to lower accuracy. The confusion matrices show that not accounting for heads versus tails leads to poor results. We speculate that also identifying the rotation of coins will lead to improved accuracy. Second, YOLO is a big architecture, so further refining the hyperparameters would take a long time. Next slide, please. If we could go back in time, we would change 3 things. First, better communication, so we don't end up redoing each other's work. Second, we would organize better, so our code is easier to share with each other. Finally, we would try to find and reuse code for other people. That's it from us. Thanks for listening, guys. CabbageJumbleAya out.
Great. Good timing. Nice work, actually. It seems like you created a problem and focused it and built all your own data. That's really admirable. You created all your own data and then augmented it. I don't have that many questions, actually. Only one really. It seemed like at one point you did show in your augmentation that you, over here, that you took pictures on an angle. Is that right?
It wasn't intentional, but there's some little angle skew for some of the photos.
And so your augmentation didn't add in angle or anything like that, did it?
No.
Pretty hard to do, actually. That's a 3-dimensional thing. Okay. I was just curious about that. No, nicely done. It's it seems like you chased it down a couple different ways on the baseline and then with YOLO. That's great. Right. Ash, any comments?
That was really good. It was, like Professor Rose said, you specified a very strong problem and you tackled it in a very strong way. I don't really have any comments per se. So I pretty much, Professor Rose kind of asked what I was going to ask about the skewing. So yeah, it was great.
Yeah, Ash, don't forget to turn your camera on, I think, if you can.
Oh yeah, sorry.
Yeah, any questions or comments? I said early on, last day I forgot to ask for comments from other people. Let me just open the floor to questions or comments from the class, actually. Now, I know you're shy about that, but if you've got something, go ahead and ask.
Quick question, actually. How did you guys choose to use YOLO as a model?
Okay, you can go ahead.
Go ahead.
Yeah. Okay,
Go ahead.
So basically in our first presentation, we suggested we were going to use an architecture very similar to our baseline, but then Ash actually said to research YOLO. So that led us down the path, and we realized, YOLO is definitely the way to go. It's state of the art, as EBL mentioned. And so you could see our baseline had really poor results because it was a pretty small network and there was all this rotation on the coins. So it's trying to classify all of these as the same thing, which is not very doable, but YOLO's a big architecture, so it was able to do that a lot better. I don't know if EBL has anything to add.
But you just said it pretty well. Yeah.
Great. Any other questions, thoughts, ideas, suggestions, compliments? All right.